Hi, people. Welcome to the last and final KTS session on reinforcement learning. The session will be taken by me and Pakshal, and we hope to go over a few topics here, including Q learning, temporal differences, Monte Carlo methods, a little bit of dynamic programming, and mainly Markov chains. Right. So let's get started. So, what is this reinforcement learning? I mean, you keep hearing about agents and how they can perform actions, but what is this field and why is it really necessary? So, I'd like to quickly take you back through to the first slide of the first KTS session. So, Vedant was explaining how there were three flavors of learning: supervised, unsupervised, and reinforcement. Right. So, in supervised learning, you have context, data, and target pairs, and you would like to approximate these to give new data and get the target for that data accurately. In unsupervised learning, the model is basically performing data analysis on its own without giving it any labels specifically. Now we come to reinforcement learning. So the reinforcement learning, you don't have anything such as a label and a pair or things like that, but it's a backbone of how you have bots for many games. They all follow reinforcement learning, and what reinforcement does is actually in the name. It tries to reinforce the model's good behaviors and tries to punish it for, or reward the model's good behaviors and tries to punish it for its questionable or behaviors that we don't want, right? So you have something called an agent. I'll explain what that is in a little while. And it learns to interact with this environment and perform certain actions. And when it using certain policies. So all these terms will be explained. And based on whatever it does and where it is, or in which particular state it will be receiving either rewards or penalties based on its actions, right? So yeah, so reinforcement learning is basically what enables AI systems to take actions in a dynamic environment. And what is this dynamic environment is basically the you can think of it this way. Let's say the model does some particular action and it moves from one state to the next state, like over here, right? Then there is a reward associated with that, and it learns about the new state and now tries to perform another action on that state, right? So based on its previous action, its new state is defined, right? That is one thing. Another thing is basically there's no such thing as a proper loss formulation or things like that, right? So our reward is basically going to act as a loss, an inverse loss function in some sense. I'll come to that. And our aim is to use trial and error and to let the model or to let the agent learn in this environment based on the feedback it receives for doing its own activity. So that is the dynamic environment. So why do we even need reinforcement learning there? So there are four main reasons. The first one being autonomous learning and dynamic adaptation. So as I told you before, the next state of the model depends on what action it chooses to perform in the previous state, right? So after that, it again has a bunch of choices to take up, let's say. And it has to adapt to its previous mode. That is, it's not defined by a fixed path. Let's say it chooses its own path. So dynamic adaptation is a key upside of reinforcement learning. Right? Next is it's good for sequential decision making, because this is related to the first part again, that anything that the model does, its next state is going to depend on the previous, right? So and the fourth one over here, which is real-time decision making, is also linked to this same idea itself. But I would like to focus on the third idea because this is key to RL, and that is something called exploration versus exploitation. So let's say you have you're investing, okay, in the stock market. You're investing. You could either put your money in a stock where you would quickly get some gains and then sell the shares and get out, or you could put in something that is expected to grow over the long term, right? And then make your money. So, but in either case, you wouldn't be really sure what you're going to get. You would be sure in the case where you put your money and quickly get it out because you're seeing the stock rise or things like that. But it's basically like a game of chance. So this exploration versus exploitation is a similar thing. So if you let the model see, if you want an immediate reward, right? You just want the model to pick the reward that is the best in the next state, which is basically like you have a bunch of rewards for a bunch of states that you can go to in the next part. You just tell the model, see whichever is maximum, give that to me now. I want to make the most reward now, not in the future. So even if the model selects, let's say there were -2, -3, and 5 were the rewards that it had to go to a particular next state, the model would choose 5 and it won't think about it much, basically. That is exploitation. Just exploit the next state and keep moving, go there, do the same thing. This exploration is something that is, you can say, what makes the model a little bit more far-sighted. So even if you had -2, -3, and 5 here, if choosing -2 in this state meant that I could choose a 10 in the next state and essentially get a +8, the model would do that. It wouldn't focus on near sightedness, so just grabbing the, or just greedy grabbing the reward that awaits it in the current state, right? That idea is key to RL. So we'll keep this in mind. So what is this agent I've been yapping about for the past 5 minutes? This agent, or an RL agent, is the entity that interacts with the environment. Remember, you're not going to be the one taking the decisions. It is some program that is going to be taking in all the environment variables, thinking about what decisions to take, and performing those actions and exploring the environment, right? And as it does this, it is going to receive rewards as a result. And that reward is going to teach it what it should do, what it should not do, right? So why am I taking chess or Go here as an example? Because you might have heard about AlphaZero or AlphaGo. They were all reinforcement learning based algorithms made by Google DeepMind in 2015 and 17, I believe, that actually outsmarted the best players in the world at their own game. There's a really interesting documentary on AlphaGo. You can watch it on YouTube if you like. So I've been talking about this idea of a state for a long time as well now. So what is this state? States are basically finite set of situations that the agent can find itself. So let's say you're playing a chess game, right? Assume you're the agent for now. Let's say you're playing a chess game and you have a particular a set of pieces on the board, right? And it's your turn to play. So you're in that particular state. You have to make a decision now, which takes you from that state to a different state. And how do you go to that different state? You move a piece. So every different configuration corresponds to a state. Right. So now let's come to the key idea that I want to talk about, which are Markov processes. So you might have heard about Markov chains. They are basically probabilistic models that basically it's almost the same. You have a state and then you have a particular probability that you would go to the next particular state, right? And you have multiple such states. Here also it's the same thing. So what the Markov property states is pretty basic. What it says is that the Markov property states that the future is independent of the past, given the present. Now, I know all kinds of tenses appeared in that one statement. So let me explain. It's basically saying, I don't care how you arrived at the given state you arrived with respect to what I'm going to go to. So basically, if I'm at a particular state ST, right? If I'm at a particular state ST, and I want to move to a state, one of many states ST+1, right? It doesn't matter how I arrived at the state ST. Once I have arrived, it means that my decision is only going to be on the state and the rewards I'm going to get in the next step. I don't care how I came to that state. Now, does this tell you something about any Markov state? Anyone wants to answer? Any property about a Markov state? If you raised your hands, I can't see, so you just go ahead and say it.
Memoryless?
Yeah, in some sense. So basically, if I were to sum that up, I would say that any Markov state basically contains all the information that it needs to about its past. So it doesn't need to depend on the past, right? So yeah, so next we come to this idea of a state transition matrix. What is the state transition matrix? Is you have a state and you have a bunch of possible next states, right? I will show you a diagram in the next slide probably, which will help you better picture this. But let's cover this and then go there. So the state transition matrix basically says, given your current state S and your next state is one of many states S prime, right? What is the probability that you'll go to each of those states? You put that for all states in a matrix and you get the state transition matrix, right? So this basically gives you the information of if you look up where you are and where you want to go as a possible next state, then you will understand that this is the chance that I can actually go to that state, right? So a Markov process is basically one that consists of a set of Markov states. So what is a Markov state? A Markov state is what we looked at before, which was basically saying that it comprises of all the information of its past, and it's one from where you can go to the a set of future states, let's say, right? So these a Markov process is basically a set of states that are interrelated via the state transition matrix. So S or the current S is a set of finite states, and P is your state transition probability matrix, right? So it's called a Markov chain also sometimes, and that would make sense. So I'll just draw an analogy to something that all of us have read in 8th standard, I believe. So food chains and food webs, right? So we'll come to something later that you'll see will look like a food web, a set of all states and all the connections between them. So if you can traverse through a particular set of connections and reach something known as a terminal state from where you can't go anywhere, basically, it means that that was basically a food chain, right? In the food web, like that, it's a Markov chain. So this is what I was talking about. Maybe this will help you get a better idea of everything I was talking about for the past 15 minutes, right? So don't mind the names. Okay, so the probabilities that you see are what is the chance that we move from this particular state to this particular state. Since there's only one outlet here, or one possible next state, which is from pass to sleep, the probability is 1, right? And similarly, since from class 3 you have two choices, either to go to the pub or to go to pass. They both have their own probabilities, which totally sum up to 1. So each of these things is a state. A circle or the square in this case is a state. And why is that thing in a square? If you see, that is what I was talking about, known as the terminal state. From the terminal state, if your agent, let's say it starts at class 1, okay, decides, okay, let me go to Facebook, 0.5 probability. Okay, let me come back with a probability of it also tells you something interesting about this. No, if you go to Facebook, you keep staying on Facebook. That is 0.9 probability. So at some point, you jump out of Facebook and you come back to class 1. Class 1, you go to class 2. From class 2, you go to sleep, let's say. If your model finds that you go to sleep is the terminal state. Basically, you're dead in this case, right? So your model can't go anywhere from there. That is what I wanted to say here, right? So yeah, next you come to something known as an episode, and this episode is basically a Markov chain. But an episode, what is different from a Markov chain and an episode is that an episode has to end at the terminal state. And a Markov chain need not, but an episode can start anywhere. Okay, you needn't even start at class 1 because it looks like there's the most entries maybe, but you can start anywhere. You need to end at sleep. If you end at sleep, it's an episode, right? So you had an episode, and then your model starts learning with a different origin problem. So now that we've covered the basics of a Markov process and what Markov chains and episodes are, let's go to a Markov reward process. Right? So Markov reward processes are basically a slightly complex version of what we've seen so far, which is going to help quantify to our agent, is what it's doing favorable or not. So you add a reward, but don't stop there. Add a discount factor also. Now, what is this discount factor? Is it's how the model balances exploration versus exploitation, which is this key idea we've talked about in reinforcement learning. So first, let's look at a reward, right? Previously, you used to have only this tuple of S and P, where P is the state transition matrix and S is the set of states that you have. So by set of states, I just mean everything that was in a circle or a square in that previous diagram. We'll take that as a reference example. right? Now S is a set of finite states. P is a state transition matrix, like we've looked at before. The two new things you add are a reward function R, right? And this reward is basically, we'll get to it, but it's an expectation of what you can achieve over going to any particular state probabilistically in as the next step from the particular state S that you're in. And this discount factor is going to be how far-sighted or near-sighted your model is, or in other words, do you want to explore or do you just want to exploit the situation? Right. So rewards and the discount factor. So rewards are the feedback that it receives from the environment. The agent receives from the environment. So in any state, right? If the model were to move to a next to a particular next state, if let's say I tell it that then if you go to the next state, you get a -2 reward, and for some other state you get a +5 reward, the model would, in a greedy approach, want to prefer the +5, right? So it's a way of telling the model, are you doing what I want you to do? Are you learning what you should do and what you should not do? Right? But it's not always greedy, and that is where the discount factor comes. So the discount factor is a hyperparameter, which means that you need to set its value, and the model is not going to, it's not going to be a learnable parameter, right? So this controls the foresightedness of the model. So the more the discount factor, the you can say the more the discount factor, so the discount factor is basically going, the more it is, you are going to have more weights on the future rewards, right? So you basically start at some particular state S, right? Let's say you start at class 1. Okay, so the reward here is -2. You start there, so forget about that. Now there's a 0.5 chance you go to Facebook. And if you go to Facebook, the reward is -1. And there's a 0.5 chance the reward is -2 if you go to class 2. So what is the average or the expected reward that you would get from the state by going to any next state? It's going to be -1.5, because it's probabilistically half of -1 and half of -2, right? So I'll just take you back here. And so the discount factor, what it's going to do, if you're going to go from class 1 to class 2 to class 3 to pass to sleep, what it is going to do is it's going to take the next reward as it is. It's going to take the next to next reward, right, with the discount factor multiplied. So it's going to reduce that reward by the discount factor, and the next one by discount factor square, and so on. Why are we doing this? For 2 reasons. Okay, so one is you want to keep total rewards finite, because if you have a large number of states and you keep cycling through them, you don't want to keep adding things, because see, whatever is in the future is not confirmed. It's still only if you go via that particular route. That is one reason. Another reason is, as I've already told you, the near and far sightedness. Right? You need a way to control whether the model should explore or exploit. So if you want the model to explore, just keep telling it, okay, see, wherever you go, just keep adding that reward to yourself. And even if that reward is 10 steps away, give it the same weightage as if it was in the next step. But that was just if gamma is 1. If gamma is 0, you're just telling it, I don't care what the reward is in the next to next step. Whatever be it, I'm just going to multiply it by 0. Whatever is in this state, you just give it to me. That's why I'll take that and go. So if you're in class 1, you just go to Facebook and not go to class 2. Right? That's how that looks. So another interesting thing to note is here there's a +10. So if your model were to have a small discount factor, it wouldn't even consider that +10 because it was 3 steps away. So it's going to do 1 by, let's say my discount factor is half, it's going to be 1. It's going to do 1 by 8 of the 10. That is no match to the -2 and the -2 by 2 that you'd be getting already. Right. So here's where we come to returns. A return is the total discounted reward. So what do I mean by the total discounted reward is this is where the discount factor comes in. I keep multiplying by the discount factor for every extra step I take to reduce the impact of that reward, which is let's say k steps away. Right. So I don't want the model to consider usually with the same weight a reward that is 5 steps away rather than one that is 1 step away. So values of gamma near 0 lead to myopic evaluation, which is short-sightedness basically. and values of gamma near 1 lead to far-sighted evaluation. So as I told you, the model in the kth step would take a reward of plus 10 to be seemingly equal to a reward of plus 10 in the very next step. So it doesn't matter the order in which that happens in if gamma was 1. So yeah, so an example return would be, I'll just show you here. Let's say I went from class 1 to Facebook again, and then to class 1 back, right? So for that, an example return would be, let's say with gamma equal to 0.1 or 0.5, let's say. So I went here. This is -1, right? But it will be taken as it is. Let's say I decided to go here first. It's -1 will be taken as it is. Then you need to take 0.5 multiplied by 0.9 because I want to stay at Facebook once. And then you need to take the next reward, which is -2 over here, and then multiply by 0.25. Yeah. So that's how it works. Right? Yeah. So the next is value function. What is a value function? A value function denotes the long-term value of the state. So if you're it's a function of a particular state. So for every state I'm in a Markov reward process, what is the expected return if I start from a particular state? So it is the expectation of the return given the state, right? So if you're interested in long-term rewards or gamma, which is higher, then you should be interested in a value function for the state. I'll stop here and pause for doubts. If you guys have any doubts, you can let me know. I'll take that as a no. Right. So yeah, so let's continue with the Bellman equation. The Bellman equation, you'll hear this name 2-3 times, is basically a way to calculate state value function. State value function was what? The expected return over that state, right? So this is the return expectation over the state. So if you look at the return, it's just going to be the return in this particular state with discount factor times return in the next step plus discount factor square times return in the next step, and keeps going till you reach some terminal state, or anyway gamma is going to kill it if gamma is not 1, right? So this second part, if you take a gamma out, this just looks like t replaced with t plus 1, right? So that is what it is. So it is the return in this next state plus gamma times the expectation of returns in the next to next state. And this, if this is what we're writing as v of s, then this is what we can write as v of st plus 1. The next state, basically. The next time. So you get this, which you can beautifully write using matrices as v is the return in this state plus gamma PV, where P is the state transition matrix. Because if you multiply this, if you multiply these two out, you would see that that is basically the chain that you're going in. Yeah, and this is pretty easily solvable. Just take all v terms to one side. Remember, this is not 1 but I because matrices, and just take the inverse. So now we found something. We found that given the rewards at all steps and the probability of movement between them, that is a state transition matrix, you can get a value for each current state given a hyperparameter gamma that is also there. So you can that serves as a way to quantify how much can you get out of that state on some kind of average, right? Yeah. So now let's move to Markov decision processes. These are slightly different from Markov the processes of Markov reward that we looked at till now. So Markov decision process is basically nothing but a Markov reward process, but now the model has an ability to make decisions based on the actions. So that tuple just keeps expanding as you see. We started with SNP, and that was called the Markov chain, right? Then you have then you added a reward and discount factor to account for a way to quantify some kind of loss function, you can say, and a way to add some hyperparameter in order to adjust the foresightedness or nearsightedness. Now we had a set of finite actions, right? That if you're in this state, you can do the following. That is basically what an action is, right? And yeah, so it's again mostly the same things. And then now the reward is just you have another index here for the action, given that the action is 80. Um, Given that AT, the action at a time t, is small a, basically. Right? So what are actions? Actions are set of decisions available to the agent to perform, which means if I'm in a particular chess game, actions are going to be valid moves that I can do. Right? So yeah. So this is a Markov decision process. So for this decision, and for this decision, you get a reward like this. So that is what is here. Yeah. Then let's have one more thing called policy. A policy is basically how do you want the model to behave in some sense, right? So I'll give you an example, and you'll understand this better. You have seen this before. That do you want the model to take a greedy approach, or do you want the model to um, always it's better to give you an example in sense of a game. Let's say two people are playing, and they can do either they have two buttons to press. It's like split or steal. Okay, so the first guy presses yes. It is yes and no. So the first guy presses yes, and the model basically observes whatever the other guy is pressing, and if a particular pattern follows, the model starts following its own pattern. That is a policy. Like always default is a policy. So just keep pressing the no button, whatever the other guy presses. Always say yes is another policy. Just keep pressing yes, whatever the other guy says. Like that, press yes and no alternatively. Press yes only if there are two consecutive yeses by the opponent player. Things like these are policies. So it governs how the action is, what action should be taken, right? And this leads us directly to the fact that policy fully defines the behavior of the agent. How you want the model to behave is going to be governed by the policy, right? And that is a distribution over all over actions given the state. Right? So two new things here will be the state and action value functions. The state value function is similar to what you looked at before, except you add one new thing, and that is that it has to follow a particular policy, and policies are denoted by pi, right? So expected return is again the function that is quantifying, but now given that it follows a particular policy, that's the only thing that's new. Again, same state, same expectation of rewards, except we follow a policy and then expect the reward, right? So that governs your action. And the same thing for action value function, q pi. And this is a function of S and A, where A is the action and S is the state, right? So this is again most of the same things. Expected return starts from a state S, follow a policy pi. Only new thing is you need to take a particular action A. I hope that's clear. So the Bellman expectation equation. This is again mostly the Bellman equation that we saw before, except with policies added in and actions added in. So this equation is used to calculate the value function of a state, given that it follows a particular policy, right? And now, again, just like before, you could express that as an immediate reward and then an expectation over returns in the next step, right? Like taking gamma outside and waiting for the return and getting the return. So this is the same thing mostly. So you take the reward for the very next state out, again following the particular policy, and then discount factor times the state value function, given that it follows the particular policy, which is v pi for the next state. And if you decompose this, you will get the same thing as what we did before, except with the new things being the policy and the action, right? So now let's get to the actual business, which is we want this model to learn this environment. So this optimal value function for a state S is denoted by V star of S, which is like saying, I'll give you any policy that you want to pick, but you will be in a particular state, right? Just pick the policy that gives you the maximum return. That's it. That maximizes the value of the state value function given a particular policy, right? So you get to pick the policy, Just pick the policy that gives you the maximum returns or the maximum value of this function. That's it. And the same thing for the action value function as well. I'll give you the freedom of picking any policy. Okay. But you are in a, but for the given state and action, you need to give me the maximum action value function over all policies. And this part is pretty obvious. So if you pick, I'll actually come to this before I come there. So you pick the best policy, right? Just apply a binary mask on it and you would get the optimal policy, which is the one that maximizes the optimal value function. And now coming to this, these are two trivial things, I'll say. So policies are ordered based on their value functions, which means that if you're in a given, let's say I give you a state, right, and you get the optimal value function for all policies. And policies are, remember that model scenario, which is when does the model decide to default, when does it decide to give a yes, and that is totally based on could be based on whatever the other user decides to do. If he gives 3 yeses, you could give a yes, things like that. So those are policies. So a policy is said to be greater than another policy if its value function is coming out to be greater than the other. Basically, I'm saying if you get more marks than me, you're better than me, which is how they define it. But right, so and in a Markov process, there exists a policy which is greater than or equal to all other policies. It's like the law of trichotomy, which is basically saying given two numbers, they can either be less than, greater than, or equal. That's actually a real thing, by the way, not making that up. Right, so we've covered this, and yeah, so I'll just briefly touch upon dynamic programming and then hand it over to Pakshal, who will be taking 3 more important topics. So dynamic programming is, first of all, a general algorithmic technique. It is not an RL specific thing, right? It exists in CP as well. So what you basically do is in 3 parts. You break it into overlapping subproblems. You solve each subproblem only once, right? And then you use smaller problem solutions, or overlapping problem solutions, to get a bigger, to get the solution to a bigger problem, which is your original problem. So this is something in algos. Yeah, so in RL specifically, what dynamic programming does is, given the full MDP model or the Markov decision process model, which is it needs to be given. Okay, there's no training that can be done there. You need to give it. Dynamic programming is applied to compute the value functions and derive optimal policies, right? So what is the optimal policy? One that maximizes your optimal value function. So you're allowed to choose a policy, and whichever maximizes is the optimal policy. Remember the binary mask, that one. Right. So the idea behind DP is this. There are 2 properties: optimal substructure and overlapping subproblems. So the second one is slightly easier. Many subproblems of big complex problems are reused again and again. So if you find a solution to them, you find a solution to not one but many problems, parts of many problems actually. So in RL, the value of a state is needed repeatedly when evaluating or improving policies. So if you find the value of that state or the value function for that state, then you can reuse it over many times. That doesn't matter what path the model came through or how many time steps it took. That doesn't matter, right? So, and the first one is optimal substructure. Optimal substructure basically says that the optimal solution to the overall problem is going to depend on the solution to the subproblems, which is like saying you solve each step optimally, then the total solution is going to be what is optimal. Is going to be the optimal solution for the full solution, right? So, and yeah, and how this works out is that the values of state S depends on the values of the next states. Yeah. So how does dynamic programming solve an MDP? So there are 4 things here. This is what we already looked at. So there are 4 things here. The 4 things are policy evaluation. Right? I won't go into the math too much and bore you, but it's again going to be most of the same stuff: Bellman expectation equations, and something like the EM algorithm, you can say, something like expectation maximization. Right? You keep repeating 2 steps again and again till one of them converges and the next one stops automatically. right? So policy evaluation, policy improvement, right? And then you have this is basically what happens. You keep repeating. So initialize with some policy, evaluate the value function using that policy, then improve the policy using the value function, and then stop when the policy converges and you've got your optimal policy. Right? So something on the lines of expectation maximization. Can I continue?
Yes.
Yeah, and the last part or the fourth part is value iteration, right? So yeah, so then there's the Bellman expectation equations in dynamic programming, which is sum over all actions that you take, right? The policy given that action and state into the expectation, basically, which is that remember that taking out the reward for the previous step and then getting discount of the subsequent state. That is basically what you get here. And you find the optimal policy using maximum overall actions.
S dash are the previous states or the next states?
S dash are the next states.
Yeah, okay, cool.
Wait, again, I'll interrupt over here.
Yeah, yes.
Yeah, in this equation again, like if you see over here, it's written, the pi is written as a probability equation, pi of A given S. So this is a general formula for pi. Like pi is usually defined to be a probability distribution. Like my policy will be a distribution, like 50% times I will go to pass, 50% time I'll go to study, something like that. But if you see, even in over here, the optimality equation, like even if we think about it intuitively, the best method is only one, right? Like you cannot depend on chance to to get your to maximize your returns. The best policy has to be something which is not probabilistic but deterministic. Like in this case, in the optimality equation, it is mentioned that we just take the maximum, the equation giving us the maximum, the action giving us the maximum value, right? So similarly, the what we will explore in the further slides will be just the deterministic pi equation. Like my policy will be deterministic and not probabilistic as in this. But yeah, the general equation is given over here, which takes pi as a probabilistic value. I hope that's clear.
Yeah.
Yeah. Also, just one thing, Smithali. So I think you are the one who asked. S dash should be the next states because your Markov definition states that once you've come to a particular state, you don't care about the past. You only care about the future. Like your past can't affect you anymore.
You talked about some previous state on the same line, so I just wanted to confirm.
Yeah. So over to Pakshal to continue with Monte Carlo methods.
Yeah, so I'll share my screen. Yeah, can I even see my screen? Hello, is my screen visible?
Yeah,
it's visible.
Yeah,
Yeah. Okay, so dynamic processing was dynamic programming was one of the methods to find this QV functions. So okay, coming to the basic idea, the main motive of all that we discuss from now on will be to find this optimal values, and if we can find the optimal V, we can also find the optimal Q. And if we can find optimal Q, we can also find the optimal pi, or the optimal policy, the best policy that could be used in that situation. So all the further discussion will be based on that only, how to find that optimal pi. But as discussed in this dynamic programming part also, that it is not a straightforward thing to do. Firstly, like if you see this, you get this equation, and you will get n such equations. If there are n states, you will get n such equations, one for each state. And there are n variables. All these v pi s are variables, right? So there v pi s will be variables. So there will be n variables and n equations. Theoretically speaking, you can solve them to find the optimal v, like to find the v for the given policy, then you can improve it using the policy improvement algorithm, like as I explained. Then you will, like, you can do it iteratively to finally converge to a solution. That convergence is promised by mathematics. I don't know exactly how, but yeah. So now we will move on to find there are limitations of this dynamic processing. First, the first limitation is that the environment may not be fully known. For example, in this method, we assume that we know this P matrix. P is the probability matrix. Like suppose I am on class 1 and I chose the action to be study. Then there might be cases where I go to class 2. There even might be cases that I go to class 3 directly. Like I made an action, but that action, the result of that action, the next state which I get from that action might be probabilistic. So this P denotes that only. Like I am on state S. I chose the action A. What is the probability that I'll go to S dash? Okay, so yeah, so this probability matrix may not be available to me at all, especially in the real world scenarios. In most games and all, this P is like it is kind of identity matrix only, because mostly if you select an action, if you click right in a Subway Surfers game, you are going to go right only. You can't, like, it cannot probabilistically land you on some train or something. So in games or things like that, this P is mostly an identity matrix, like it is known at least. But in real world scenarios, P is not known, so we cannot use that method. Another limitation is, if you saw in DP, we have to solve n equations, where n is the number of states. Now there are several, like game of backgammon has over 10 to the power 20 states. Then chess has even more, I think, some very large number. So even if we have value iteration update on a million states per second, it will take over 1,000 years for modern computers to complete a single policy evaluation task. So these are the main reasons why DP is not always preferred. Like we for small tasks it's okay, but for larger tasks we can't rely on DP. So we come to Monte Carlo methods. So again, Monte Carlo methods are not specific to RL. They are like very commonly used. This is the Wikipedia definition. They are a broad class of computational algorithms that rely on repeated random sampling. Like mainly whenever we assume that sampling randomly over the large number of time, the average result will converge to my actual result. That is called Monte Carlo. In just rough terms, like just layman terms, I'm saying that is the main concept behind any Monte Carlo experiments. So over here, what we are trying to do is we will conduct multiple episodes of the model. What do I mean by episode is I'll start the model at some fixed starting point or some random starting point, and I'll let it and I'll give it an initial policy to start with. Now, following that policy, the model will automatically choose some actions. It will go to some state, then it will again choose some actions, go to some state, and so on till it reaches the terminal state. Terminal state is the square one, which was mentioned as sleep in that example. So that is what I will allow the model to do. That one thing is called the episode. Now, once an episode is completed, I can actually find the exact return value. Return value is GT, if you remember from the previous slides. After the this GT is my reward. So it is the reward I get in the next step plus gamma times the reward I get in the further next step, and so on till the last step. So the value function is nothing but the expectation value of this thing. So what I can do is expectation value. Okay, wait. Is everybody familiar with the term expectation? If anybody is not familiar with the term expectation, can you please raise your hand? Okay, cool. If everybody is familiar, then fine. Yeah, so expectation value of this, if you know the law of large numbers, it says that if this is a random variable, say, then if you take lots of readings, like lots of random samples, and average them out, it will eventually converge to the actual return value, to the actual expectation value. uh, yeah, given that the number of samples is very large, and yeah, it can even reduce the variance of that thing and all. So yeah, so over here what we will do is we will hope that if we take multiple number of iterations, multiple number of episodes of a particular policy, I will eventually converge towards the actual optimal value. Okay, so yeah, this is in accordance with law of large numbers. So okay, first of all, okay, coming back to what I've written, GPI over here. GPI is nothing but generalized policy iteration. Mainly the two-step process, which was discussed earlier, calculating the value of the value function when a policy is fixed, which is policy evaluation, and then improving the policy, which is called the policy improvement. These two steps together are called, in that case, it was called policy iteration. In the general case, it is called GPI, because like suppose I am tweaking something in with this policy evaluation task, I can still, like, I can do policy evaluation in some other method as I am discussing now. So that's why it is called generalized policy iterations. So yeah, so there are two steps: policy evaluation, policy improvement. Policy improvement was a simple step, if you remember. We just have to I have all the values, I just have to change my policy to select the best action, the new best action. Yeah, so that was policy improvement. Policy evaluation was the one where I needed to solve all those equations. So I am trying to replace that step with Monte Carlo methods. So yeah, this is what I explained just now. The value is nothing but the expected return. And yeah, so what I can do is I can run an episode. I will get, like, after an episode ends, I can actually calculate the exact return for that episode at least. Now I will take multiple episodes. I'll find the return for each state in each of these episodes, and finally I'll average all of them to get my approximation of a value function.
Okay.
Yeah, so again, based on a few technicalities, there can be multiple versions of this Monte Carlo methods. First of all, see, you can visit the same state twice or thrice. So which return to calculate? Like, I suppose I started with sleep. Wait, sleep is the termination thing. I started with class 1. I went to class 2. I went to pub, and I came back to class 2. Now, uh, what is return? Return is like the average expected discounted value, uh, discounted reward that I'm getting. So if I consider my first visit to class 2, there will be some other return value. If I consider my second visit to class 2, there will be some other return value. So I can, like, what to consider. So if I consider only the first visit, it's called the first visit Monte Carlo. It is actually the most widely studied MC method. Like, after that, it becomes a bit complicated also. But yeah. So if you go through this algorithm, see, I inputted a policy. Then now I initialized the for the first iteration, I initialized the V. Okay, again I'm using V, but I can similarly do for Q also. So V I initialized randomly. I initialized an empty list to store my returns. I generated an episode. I initialized my return G to be 0. Now at each step, what I'll do is G will be gamma times G plus the, like, I I hope you get this. I am just backtracking my after backtracking my returns after my iteration is completed. and yeah, I then store it in my returns list, and then I just average it out and I update my v value according to the average. Is this clear? And I loop it for multiple episodes, so that this v value will slowly converge to the actual v. If any doubt, then please ask right now, because later things will get even more complicated. Yeah, even if you have doubts with the like basics part, the fundamentals part that was covered earlier, you can ask, because like these things are going to be used further to create more algorithms and all.
Can you like explain this algorithm once using that class example,
Okay,
like
yeah.
just to get a
So,
better idea?
yeah, wait. I'll just yeah. So, wait again. Here there are no actions. There was one with an actions also. Yeah, this one. So here I have different actions. Okay, so what I'll do is I'll first initialize my starting points. I can either do that randomly, or I can fix the starting point. Like for say if you are simulating something for a game like chess, you will have a fixed starting point. Like you cannot have some random things. But yeah, suppose I'm starting from this class 1 state. I have an the agent has two actions possible: study and Facebook. Okay, if I choose a study action, there is a 100% probability that I'll go to this state only. If I choose Facebook action, there is 100% probability that I'll go to this state only, and meanwhile I'll get my reward -1. If I choose study, I'll get reward -2. Now I have designed some policy, and I am feeding that to my like my agent is now going to follow that policy. Like if you remember the thing, I initially start with random policies, but then I slowly improve them over the number of steps, and then finally go to some bit. Okay, so I started with my okay, my policy is to first on this state my policy is to study, on this state my policy is to study, on this state my policy is to study and reach this terminal state. Okay, so this is my policy. Now I'm following this policy starting from here. So starting from here, I chose study, I got -2 points, and I went over here. Then I again chose study, I got -2 points, I went over here. Then I again chose study, I got +10 points, and I went over this terminal state. Now I'll backtrack my results. Okay, so now what is the return for this this state? The return for this state in this example is +10, right? Then return for this state in this example is is 8. Like return, if you remember, return is the okay, again here I am choosing gamma value to be 1. Return is the reward I got in this the next step, plus gamma times the reward I got in the next step, plus gamma square times the reward I got in next step, and so on. So over here my reward will return will be 10, here it will be 8, here it will be 6. Was this clear?
Yeah, yes.
Yeah, so I got my returns. Now obviously my value function is nothing but the expected value of return. Okay, let's not go to the vpy function, let's go to the qpy function. Qpy is the expected value of return when I started following taking that action and following the policy pi. So my qpy value, it is the expected value. What I can do is, see, I made this episode once. Now I can make some other episodes, say like I okay episode in the sense, oh okay, over here it won't be possible, like all episodes will be the same only. but there might be cases where it is a probabilistic thing. Like if I choose study, there is 50% chance that I'll go over here, 25% chance that I'll go over here, 25% chance that I'll go over here. In that case, I need to take these multiple readings, multiple episodes. I'll find the return values for all these particular episodes. Finally, I'll average them out. And I'll say, according to the law of large numbers, this average value should be nearly equal to the expectation value. And therefore, it is equal to the Q pi values or the V pi values, whatever. Was this
Yeah.
clear?
Got it.
Yeah, so this is Monte Carlo methods. Okay, again, now what we discussed just now was first visit Monte Carlo method, in which I just, okay, in this case, I did not return to some place again. Suppose I, from here, my policy is such that I'll go from here to here, then again to Facebook, then quit, then study, then again come back, like something like a cycle. In that case, I will have multiple return values. Like the first time I came here, my return was something else. After going over Facebook and coming back, my return will be something else. Is that clear? Like my returns will be different every time. So
Yes.
if I'm following first visit Monte Carlo, I'll just consider my first return value for the averaging and tasks like that. Now there is the next class of Monte Carlo methods is every visit Monte Carlo. In that case, I will consider my every visit and average all of them. Like suppose I came the first time over here, my return value was 6. Second time I came over here, my return value was 4. Third time I came here, my return value was 2. So after completing all my episodes and when I will be updating my value function, I will neither write 6 nor 4 nor 2. I'll write the average of all of these. 6 plus 4 plus 2 divided by 3, which is 4. So yeah, I'll write 4. I'll just go back to that slide also. Yeah, and yeah, this algorithm is also written similarly, only the same thing which I explained just now. You can go through it later. Yeah, now we come to a different class of Monte Carlo. Monte Carlo only, but a kind of a different algorithm. Over here, if you see, whenever we did, what we did was after a large number of steps, I updated my value function with the average of the return values, right? So here I was like directly changing my V value after each iteration, after each episode. Here, what I'll say is I'll not update my V directly. I'll just do something kind of a gradient descent thing, not a gradient descent. Yeah, but this is my learning rate parameter, a hyperparameter which I can control. And this is GT minus VST. Okay, so V was supposed to be equal to GT. Like it is supposed to be the expectation of GT. So however much was the difference, I'll just keep on adding these error with a learning parameter alpha. Like similar to gradient descent, what we do. I am kind of updating my VST slowly. Now again, what will happen is I'll conduct an entire episode. I'll find all these GTs, and then I'll update my ST with this after the entire episode. Then again, I'll conduct another episode. I'll again make such updates. Again, I'll conduct another episode. I'll make such updates. And after a large number of steps, large number of episodes, this algorithm will also converge to the actual value function. Again, like throughout the topics, there will be many places where I'll say it converges. It is true mathematically. Even I don't know the proof, but yeah, it converges. And like yeah, it is natural also. It should converge. We are actually going towards the correct V value in all cases. Yeah, was this part clear? Because this will come again. Yeah, assuming all of you are clear, let's move on to find a limitation. So okay, Thing is, it works well. It does not require the P matrix. It can handle even multiple states. Like I'll just randomly move on, and I can hope that all states are covered at least once. Or
Wait, so is
if
this
some states are,
kind of like a regularization?
sorry.
Is this kind of like regularization, like adding the alpha thing?
Not regularization, it's like gradient, like how regularization, like we are not, this is not a loss function first of all, so which
Yeah.
regularization are you talking?
Oh no, my bad, my bad.
Yeah, so yeah, this Monte Carlo methods like fix all of these problems which we mentioned earlier, that the environment may not be fully known, P matrix I may not know. So this says, okay, I don't want P matrix, I'll just do some random samples. I'll just sample randomly, and I'll make it work with this P matrix also. The number of states may be very high. This fights even that, like all the most probable states will be covered in these exploration episodes. Like in each episode, I'm going to explore something new. So mostly all states will be covered. Mostly. So yeah. But this has its own limitations. First of all, okay, we did everything for v values, but yeah, similarly we can do for q values also. Like it's just the same. But again, there is a limitation when we start doing it for q values. One thing is, see, if I am following a policy, I told earlier also, we will be looking at only deterministic policies. So in deterministic policy, if I am fixing a policy, I am going to choose the same action every time. So if I'm choosing the same action, how will I learn the q values for other action values, other action state pairs? Like in this case, after that class 1, I was going to study. Now my policy is to study, so I'm going to study only. Now I have no way of finding the q value for going to Facebook, because I'm not doing that only. So if I'm not if that path is not coming in my episode only, how will I learn these q values? And those q values are something I need, because if I don't know that q value, how will I know if my policy has to be improved or not? So remember, improving worked in that way only. If I see that the q value for Facebook is more than the q value for study, I will say that okay, my Facebook is more better policy, and I'll change my policy. But in this case, I won't be able to explore that path only, so I cannot learn that q value. So how to start? Like how to solve this problem? So there are main two solutions. First is exploring starts. It is a method in which, irrespective of policy, I'll always start with a state action pair. Like in all the previous cases, I was saying that okay, we start with this state, we start with some state, and then wait, what happened? Am I audible?
Yeah,
Yeah, you're audible. Yeah.
Okay, I don't know. Maybe I pressed some key. Yeah, so in exploring starts, we will, instead of starting from a fixed state, I will start from not a fixed state. Wait, instead of starting from a random state, I'll start from a random state action pair. Like I'll randomly start with class 1 and choosing Facebook. I'll start with that action pair, a state action pair, and then I'll follow my policy throughout. Then I'll not break my policy, but in the starting, the first position, I'll break my policy and I'll randomly choose some other state action pairs. What this will imply is I will get at least some readings for my other action values also, other state action pairs also, which are usually not covered. I'll get some values for them also, and over the large number of states, again I can hope to learn meaningful things, meaningful Q values for those actions also. Another example is use only stochastic policies and not deterministic policies. Like if I have only stochastic policies, I can do it. But then again, deterministic policies have the advantage that, like, I know my optimal policy is also going to be deterministic. So it does not make sense to search using a stochastic policy when I know that my answer is a deterministic policy. So okay, I'll not go much deeper into that. Like, yeah, that is this second method is another a separate topic in itself. Yeah. Okay. So till now, was there any doubt? Using Monte Carlo for policy evaluations, was there any doubt? Because now we will move on to the entire iteration using Monte Carlo. Yeah, I hope there are no doubts. So now we will move to Monte Carlo control. Like, we will use Monte Carlo methods for the entire iteration, evaluation also, improvement also, like together. By together, what I mean is, if you remember in the dynamic programming, yes. Okay, fine. In dynamic programming also, we had a iterative algorithm for this value. Wait, I'll just show that, because Sharan went over it very quickly. I don't think you might be remembering. Yeah, over here, there was something called a value iteration. In this, what we did was we were merging evaluation and improvement steps. See, evaluation in dynamic programming, evaluation we were doing using this, solving this n equations and trying to find finding the vpi values using an iterative method. In and then in policy improvement, we were just changing our policies to move to a better policy. In policy iteration, what we said was we will start with a pi policy, then we will evaluate vpi, improve pi using this, and continue this. Value iteration, what this said was, I will perform only one iteration of this initial, like the value evaluation, policy evaluation part. This is the policy evaluation part where I am trying to find the v values given a policy. In that, I'll perform only one iteration, and then I'll move on to policy improvement part. Like, if I even if I do this, it is proved to converge finally. So similar things I'm doing over here. Here also, what I'll do is I will make this policy evaluation part using Monte Carlo control, either this constant alpha or this every visit any of the Monte Carlo methods. I'll do for only one episode. Like, one episode I'll do. I'll update my v values, and using this partly updated v values or q values, I'll improve my pi value again. So pi value, the policy improvement step will be the same. My pi next pi, new pi, will be the argmax of qs comma a, the action a, which gives me the maximum value of q, will be selected by my policy pi. I hope this representation is clear. I will make this improvement step like it's the same as earlier only. I'll make this improvement step after just one iteration of my Monte Carlo method, any of the Monte Carlo method. If you remember, all of these were iterative methods. I was taking using this law of large numbers. I was taking multiple episodes, and I was averaging and updating my v pi value to find the exact v for a particular pi. Then I was improving my pi. Then I was again finding the exact v for that pi. Now what I'm saying is, I will not find the exact v for my pi, because anyways this v is not the final one. The final v is something else only. So why waste time over here? So I'll just perform one iteration, one episode. I'll make the corresponding updates, and then I'll move on to updating my pi using this new v values. Is that clear? Yeah, this is the algorithm to do that. I'll select some random pi. I'll start with a random pi. I'll start with the random q values. Now loop forever. I'll select my S0 and A0, like the initial state action pairs. Then I'll generate episodes. I'll store my G values, and I'll store all my returns. Once I have all my returns, I'll just do this once. I appended my G to returns. I updated my Q values once, just once. And immediately after, using this new Q values, I found my new pi value. Yeah, and this is using this exploring starts method, which is nothing but basically I initialize S0 and A0 randomly so that all S0 A0 pairs are considered, and finally I converge. Yeah, any doubt in Monte Carlo control? So that yeah, then we will move on to a new method. Any doubts with Monte Carlo? Because the next method is nothing but the intersection of Monte Carlo and dynamic programming. So if both these are not clear, then that will be a bit difficult. Yeah, so if no doubts, then we move on to TD learning, or temporal difference learning. And this is actually the central idea in, and the most novel idea in reinforcement learning. Yeah, what happened to this? Fine. Yeah. So it is basically a combination of Monte Carlo and dynamic programming ideas. Like Monte Carlo methods, these TD methods can learn directly from raw experience without a model. Like I don't need a P matrix. I'll just run some episodes from that experience I'll learn. Like that is the similarity with Monte Carlo methods. And similar to DP methods, the updates will be made based on the, like if you remember in DP, my v pi for some state depended on the v pi of the next state. Similarly over here, updates will be made based on some other learned estimates. Okay, let's go to it more clearly. All these were just facts. Okay, so now, okay, if you remember constant alpha Monte Carlo, after each episode, the value is updated by this difference between actual return and the value. Okay, I forgot to mention this, but yeah, the difference between the actual return and the value is called the temporal difference, which is basically the nomenclature of this method. So, and scaled by a hyperparameter alpha. Now, I can see over here, I need to have this return value GT. If you remember this, okay, I'll just show you. Yeah, constant alpha MC. We were updating after the end of an episode. I was updating GT minus VST. GT is the return value. Return value can be calculated only after the entire episode. And this was the exact reason because of which I had to wait an entire episode. Like I have to wait for an episode to get over, only then I can update my values. Now this can be a problem if there are very long episodes, like say chess. You can have a very long chess game. Like you can have very long episodes and you will have to wait that entire episode to get over to just update your value once. So that can be a problem. So if somehow I can eliminate this GT, like somehow I can replace it with something else, this this update can be made online. Online means before the episode ends. After each step, I can make an update. Like I moved from class 1 to class 2, I'll update the value function of class 1. I moved from class 2 to class 3, I'll update the value function of class 2. That can be done if I can replace this GT values. So here, what we do is in temporal difference learning, we replace this GT value by RT plus 1 plus gamma times V of ST plus. Okay, GT is the return, expected return. Sorry, GT is the exact return, not the expected return. GT is the return. So the return is nothing but the return in the next step plus gamma times the return in the next step plus gamma square times the return in the further next step, and so on. Now, all those terms can be written as the gamma times the value function of ST plus 1. Okay, so actually, in actual terms, this should be the actual V pi, not the approximated value. Okay, if you noticed, initially we were using small v, and now we are suddenly using this capital V. Capital V is for approximate values. Whenever we are taking approximate, we are using capital V, and similarly for Q also. So actually, this should be small v ST plus 1. But I am approximating it, like assuming my V value is close to the actual V. Actually, I'm trying to update my V value to that actual V. And in doing that process, I'm assuming that my V is nearly close to that V. And I am approximating GT by this. So yeah, I don't have to wait for the episode to end if I have this, because these values are already available even in my current iteration, current episode. So yeah, this is the most basic kind of TD method, which is called one step TD or TD0. Yeah, so in this, I will replace my GT with this term RT plus 1 plus gamma times the value of next state. And this will be my temporal difference. I'll update my things accordingly. This is the, yes, basically the same. I have a policy P, some alpha, and I initialize V randomly. Then I select an action using pi, and as soon as I take an action, I got some reward at as soon as I got to some new state. I'll immediately update my previous V value. And yeah, now I will have some new S value, and I'll repeat this until I reach the terminal S. So this, the best part of this is I am updating it during the episode itself. So during the episode, if I visit that cell again, that state again, I will have the a better V value. And like obviously I'm making updates earlier, so this should converge better. So yeah, actually this converges better than the Monte Carlo algorithms. Yeah, and okay, a small technicality. Yeah, we have time, so I'll cover this. So there is something called a batch updating. Yeah, it is independent of all that happened. Like I can even skip this, but yeah, we have time. So we were calculating the increments during the episode, right? Like what we were doing this, we were updating, we were finding this temporal difference, and I was updating my V value that, immediately during the episode itself. What I do in batch updating is I can calculate this value RT plus 1 plus gamma, like this difference. I'll calculate and I'll just store it. I'll not update it directly. I'll just store it, and I'll continue with my episode, say a bunch of episodes, either one episode or a bunch of episodes, whatever my wish. That is called a batch of episode or a single episode batch. Yeah, and after that batch is completed, only after that I'll update my V value with this. Yeah, is that clear? It is different from constant alpha Monte Carlo. In constant alpha Monte Carlo also we were updating after the entire episode completes, but here over there we were updating the return value. Here we are not updating with the return value. Here we are updating with the values which are calculated during the episode itself. These temporal differences were calculated during the episode itself, but they were added. They will be updated only after the batch is processed. So yeah, this is particularly useful in the case where only few episodes are possible. Like cannot think of an example, but yeah, in those cases, what if we want to train efficiently, we will conduct the same batch of episodes again and again. So in that case, this batch updating actually helps, and the model actually converges deterministically to the same solution, irrespective of the value of alpha. So this is some interesting thing. Even I don't know what is the proof or why exactly is this more important for limited few episodes, limited episodes scenario. But yeah, this is like a technique used. Yeah, and Q learning. So again, the TD0 algorithm was shown for only V values, but it can be extended for Q values also. I'll just replace this gamma times V of S to Q times Q of ST plus 1 into 8, comma 80 plus 1. Again, Q is a function of both states and action. So instead of QS, it will be QS comma A in all cases, in all places. So if I have a given policy, I can learn its Q values in this iterative way. Now, again, making one more assumption. As we had made assumption over here that I can replace my GT, I can approximate it using this. Like if this capital V was the actual V pi, then this would have been true, but it is not. But I still approximate it to that. Similarly, over here, this Q is actually not equal to the optimal Q star, but I want to make it. I am trying to force this Q. I want to update this Q eventually to reach Q star. I can for now I can assume this to be Q star itself. This Q is Q star itself. In that case, this Q star. Okay, so what is Q star S T plus 1 comma A T plus 1? It is the what do I say? That the action which I'll choose, the state action, the Q value of the state action pair that I'll choose for my next iteration. And in the next iteration, what I'm going to choose optimally is going to be the action which is going to give me the maximum value. So like yeah, if you remember, the Q star optimal policy was given to be defined like this. It is the maximum possible value of Q for the given state over all its actions A. So just I'm assuming Q star to be equal to Q, and like I got this formula. I just replaced it over here. So what I'm actually doing is I am combining my policy evaluation and policy improvement steps together. And like, yeah, essentially we are formulating our guess using another guess. So it is not intuitive, but yeah, still this converges. Like finally, after the large number of iterations, this will converge to Q star. All my Q values will be the actual Q values that should be there. Yeah, and yeah, in this case, the learned action value function directly approximates Q star, which is the optimal action value function independent of the policy being followed. So here, if you recall, we are like, I'm not mentioning policy pi anywhere. Like this Q pi, this capital Q is obviously the Q value calculated following a policy pi. I'm not mentioning that pi anywhere, but still I can guarantee that this will converge to Q star only, the optimal policy only. So it is an interesting thing, and it is a key algorithm used in reinforcement learning. So independent of policy being followed, I am guarantee like it is going to approximate Q star only. Yeah, I have a few assumptions. Like I have a few prerequisites. First is all state action pairs have to be visited, and that is required for correct convergence. And all so the all that is required for correct convergence is that all pairs continue to be updated. All pairs should be updated. Like we cannot continuously ignore some pair and say it is not converging. And yeah, that's the only requirement. I can start with any function, any pi. Although there will be some policies which will converge quickly, some policies will take a long time to converge. Like that is obvious, but finally they will converge. And yeah, and if I obviously, and if I choose the step size parameters correctly, so Q has been shown to converge with probability 1. Okay, I hope you guys understand what probability 1 means. Like there are still some cases where Q might not converge, some very well crafted cases, but yeah, for the most cases with probability 1 it will converge. And yeah, this is my Q learning. So yeah, and okay, is there time? Okay, any doubts still here? Okay, so I will ask a doubt. We are in this case, we are starting with some S and we are choosing A from S using policy derived from Q. Now this again, I'm doing that exploring starts thing, but after a point of time, after my Q is uh, Q becomes closer and closer to Q star, the optimal Q, there will come a point where it becomes deterministic. Like I am going to choose only a single action, and other action state action Q values won't be updated at all. So here comes this thing called epsilon greedy. You remember over in that slide I mentioned two ways to mitigate this effect. One was exploring starts, and the other was to use a stochastic process instead of a deterministic one. To use a stochastic policy instead of a deterministic one. So this epsilon greedy is a way to make a deterministic process, to convert a deterministic process into a stochastic process. How? So we just take a small number epsilon. We in my deterministic process, deterministic policy, what is going to happen is one action will have full 100% probability, all others will have zero probabilities. What I'll do in this epsilon greedy method is I'll just remove some small epsilon probability from this one action, and I'll distribute epsilon by n number probability in other actions also. So all the other actions will also have a probability of happening. And I can actually say that in 1 by epsilon number of steps, they will actually occur also. So that way, if my number of episodes are greater than 1 by epsilon, I can actually guarantee that all state action pairs are visited at least once, and these Q values are updated accordingly. So that is the thing with this epsilon greedy. Any doubts till now? Yeah, this is the end. Like now I'll just go through a small piece of code. Otherwise, any doubts in the entire session? Okay, cool, then we will end with a simple example. So this is a common problem in RL called the grid world. Now I'm starting from this position, I have to reach this treasure, and I don't have to come to this wall. and in the minimum number of steps. So this I will define. Okay, so first of all, I have to define my model. So I am defining it as these cells are my states: state 1, state 2, state 3, state 4, state 5, and so on. Then I have to define my actions. Actions are these 4 things: up, left, down, right. Which are the these are the actions that I can take at any state. And these are my rewards: -1 at all other places, -10 where this wall is, and +10 where this treasure is. Again, why am I taking -1? I can take 0 also. I'm taking -1 so that each number of extra step is penalized. Like if I just place it 0, if I replace this -1 by 0, my model can just go on bouncing between 2 cells. Then finally at some point of time it will reach my treasure, and again it will get +10 points only. So that should not happen. Its extra steps should be penalized. So that's what I'm doing by this -1 rewards at each other step. If it reaches this wall, it will get -10, and if it reaches the treasure, it will be it will get +10 points, and the game will get over. Like it will terminate. Yeah. Is this problem clear? Now what I'll do is I will train a model to learn the Q values of. Okay, wait. I'll just share my code. Yeah, I hope you can see my screen. Yeah, so this is the code. So first I'm defining my board. Board has 3 rows, 3 columns. Start position is at 0,0. The win position is at 2,2. The loss position, or the position where penalties can happen, is okay, only 1 in this case, 2,1. Okay, wait. If you see the diagram, yeah. This is 0,0, 0,1, 0,2, like 0, 1, 2, and 0, 1, 2. So this is my starting position, 0,0. This is 1,2. This is 2,2. So sorry, this is 2,1. This is 2,2. So that you can see in this code also. 0,0 win position is 2,2, and the loss position is 2,1. I define something called a state. It has functions like get reward, which will like calculate the reward for that position. It will calculate if the game has ended or not. Something which if I give it what action I'm taking, it will tell me the next position. And
Wait, so there are two terminal states here, like loss and win.
no, loss is not the terminal state. Like, I can make it if I want, but in this case I am not making it a terminal state. See, if you see, the end function also defines only if my state is win position, then only it will end.
Okay, fine.
Like, yeah, in
No,
this
like
I
thought
can
it
define it
was
differently also. Sorry.
okay, got it.
Yeah.
No, I thought it was loss, so like in a way there's a way you can lose the game, I thought.
Yeah, no, it is just this. It has only one terminal position as for now. We can change that, I think. Yeah, and yeah. Oh, okay. One thing I forgot was this p values are deterministic in this case. Like if I am at this position, if I am at 0,0 and I am choosing the action right, there is only one way that I can go over here. There is no probabilistic things going on right now. Yeah, and yeah, like there may be games where these probabilistic things might be there. Like say I'm playing chess, I moved my pawn ahead. That is my action. Now, what state I'll reach depends on the move of the opponent. Now, opponent's move can be modeled probabilistically, and I can say that there is a 70% probability that the opponent will also move its pawn, 30% probability that it moves its knight, and so on. So yeah, the p values are this only, and yeah, I think we can go. Then yeah, and one more thing, if its next state is not possible, like suppose I am over here and I choose up, then I'll not go up and I'll just jump back to this position. Like it will not penalize the model. Actually, we can penalize the model also for making an invalid move. But yeah, that's up to us. Like now things like become very much in our hands. We can control the behavior that we want. And yeah, I defined an agent which has states, some actions. Alpha value is 0.5, gamma value is 0.9, epsilon is 0.1. This is the greedy epsilon wala epsilon. And yeah, we define functions to take an action, define the Q-learning algorithm. So Q-learning, how it will work is, initially it will initialize the values of Q to 0. We can also initialize it randomly, but in this case we will initialize it to 0. Now, as soon as I move from here to any position, say I move to the second position, what will happen is I'll get this reward -1, and I will immediately update my previous Q value according to the update equation that I showed earlier. The update equation is the Q value over here is going to be 0 only in all directions. So when I reach over here, the update will be only -1 times alpha, the R times alpha. And yeah, similar things will keep on happening. And yeah, I just plot it to find the reward versus episodes function also. The show values function, which shows all the largest Q values in each cell, and the final solve, the route it takes finally. So yeah, this is the training done for 10,000 epochs. And yeah, you can see initially it was getting many negative values, like it was hitting the wall again and again, -65 something, and later it learns automatically. It does not go that negative, it stays positive at least. In fact, the best way you can get is in 6 points only. Like you start over here, you get -1, -1, -1, -1, and +10. So total 6. So maximum points you can achieve in this game is +6 only. Yeah, and we can see our model achieves that quite a lot of number of times. So it is learning it very well. Now this is a function which shows the value, the largest Q values. So you can see in this wall wala cell, it is showing a large Q value, saying that a negative Q value, which says that this is not somewhere where I would like to go. And yeah, these are all the learned Q values. And like for state 1, state 2, sorry, row, column, action, that is the notation. And yeah, this is the final solution that it gives. It will start with 0, 0, it will go right to 0, 1, then again right to 0, 2, down to 1, 2, down to 2, 2, completed with a total reward of 6. Now we can actually use this algorithm to solve even for multiple board row columns. Like say I have a 5, 5 board where I start with 0, 0. My win position is at say 2, 3, and I have multiple walls, say 2, 1 also, then 3, 3, and 4, 1. And yeah, now okay, again in this case I'm getting this value. These are the Q values. Where was my this? I forgot my win position. win position was 2,3. So the third row, fourth column. Yeah, so here I have a very high return value. Sorry, Q value. These are all the learned Q values. And okay, if I wanted to solve, it will solve it in this way: 0,0, 0,1. Like so, yeah. This algorithm pretty much learns any the correct path in any kind of maze you put it in. So basically, that's the beauty of RL. I did not tell it what all states are possible, what all games are possible, what all episodes are possible. It explored them on its own, and it finally converged to the correct decision. So that is the beauty of RL. In RL, basically you can make multiple decisions, but the model has to finally learn the best decision to make in each state. Yeah, with that, we conclude the session. Any doubts? In the entire session? Okay,